Hi everybody, so we are in section 5.3, evaluating definite integrals. So we have looked at the concept of the integral in the context of that limit of the Riemann sum, right, how to compute it directly or exactly, and then we looked at approximations via rectangles, we looked at interpreting integrals as area under a curve, but now we're going to look at how we can actually compute integrals directly and a lot more simply. So to start us off, we're going to talk about the evaluation theorem. So the evaluation theorem says if f is continuous on the interval from a to b, then the integral from a to b of f of x dx equals big F of b minus big F of a, and this is where big F is any, and they got this wrong here. This shouldn't say derivative. This is where big F is any antiderivative of little f. Squeeze this right in here. Antiderivative. There we go. So this is where f is any antiderivative of little f. Alright, so what this evaluation theorem tells us is if we want to compute an integral directly, all we need to do is be able to find its antiderivative and then evaluate it by subtracting it from b minus from a. So let's look at a few examples here. So we do need to recall back to the end of chapter 4, at 4.7, we talked about how to take an antiderivative. So you do need to be able to do that in order to compute these integrals. So evaluate the integral from 0 to 2 of x squared dx. So to do this, we take the antiderivative of x squared, which you remember hopefully you add 1 to the power and then divide by that same number. So that's going to give us x cubed over 3, or 1/3 x cubed, if you'd like to say it that way. Okay, and then once we've actually taken the antiderivative, we're going to put, this is called an evaluation bar from 0 to 2. So again, this is our evaluation bar. Once we've actually taken the antiderivative. Okay, so once we take the antiderivative, then we no longer need the integral symbol anymore because we've taken the integral. And now we just need to evaluate. So this is going to be our antiderivative evaluated at 2. So that's 2 cubed over 3 minus antiderivative evaluated at 0. Which gives us 8/3. Okay, which is so much faster than trying to do a rectangular approximation, trying to find a limit of a Riemann sum, and more exact than trying to guesstimate with areas. So again, we take the antiderivative first, and then we evaluate big F of b minus big F of a. So antiderivative evaluated at b minus antiderivative evaluated at a. All right, let's look at another one. So evaluate the integral from 1 to 3 of e to the x dx. So antiderivative of e to the x is just e to the x, evaluated from 1 to 3. So that's going to be e to the third minus e to the first, which we can just write. We don't need to write e to the first, we can just write it as e. And that would be it. Okay, so no need to get approximations. Don't use a calculator for it. Just leave it exact, and that's the best way that you could write it. So we get e cubed minus e for the area under that curve. Okay, let's look at one more. So find the area under the cosine curve from 0 to b, where b is between 0 and pi over 2. So in this case, area under the curve, so that's the integral, under cosine, so cosine of x dx, from 0 to b. and b is going between 0 and pi over 2. So let's go ahead and take an antiderivative. So the antiderivative of cosine is sine, right? Because the derivative of sine is cosine. So that's sine of x evaluated from 0 to b. So that gives us sine of b minus sine of 0. Sine of 0 is 0. So we're just left with sine of b. So the area under the cosine curve from 0 to pi over 2 is going to be whatever the value is of sine of b, with b between 0 and pi over 2. Okay, so for example, the area under the cosine curve from 0 to pi over 4 would be sine of pi over 4, which is root 2 over 2. And then the area from 0 to pi over 2 under cosine is going to be sine of pi over 2, which is 1. So it's an area of 1. And you can pick any value you want from 0 to pi over 2 and get a corresponding area under cosine. All right. So next let's look at the indefinite integral. So the indefinite integral, this is really just a notational thing. So this is the notation we use for an indefinite integral. It's just an integral with no bounds. And essentially what it's doing is it's telling us to take an antiderivative. Okay? And that's really all it is. Okay, so whenever you see an integral with no bounds, we're just taking a general antiderivative. You can't forget that when you take an antiderivative, it does require that arbitrary constant, that plus c, and that's what this paragraph down here talks about. So you're going to take the antiderivative and then add c to it. Okay, and you can see down here, right, for example, the antiderivative of 1 over x is ln of absolute value of x plus c. Okay, and then we get that because the derivative of ln of absolute value of x is 1 over x. Okay, so when we don't have bounds on the integral, we're just getting out some function, that general antiderivative function, so we're not getting out that specific value, that area, like we would if there were bounds. Okay, so let's look at a couple examples of indefinite integrals. So the integral of x cubed dx. So antiderivative of x cubed, that's going to be x to the 4th over 4, plus c. And that's it. Okay, nothing too different about that one. Okay, it's just computing an antiderivative. Okay, and then for part B, integral of sine of x, well, the antiderivative of sine is negative cosine, right? Because the derivative of cosine would be negative sine. So the derivative of negative cosine is positive sine. And then, of course, plus that arbitrary constant. Okay, so nothing really new here, just the notation, right, of using that integral with no bounds. Okay. It is very important to be able to distinguish between a definite integral and an indefinite integral. So, very important difference, a definite integral is a number, whereas an indefinite integral is a function, rather a family of functions. So, when you're thinking definite integral with bounds, you should be thinking area under a curve. Area is always a number. Okay? Whereas indefinite integral is just an antiderivative, and it's more like a family of antiderivatives, right, with the c value being arbitrary. So definite integral is an area, it's a number. Indefinite integral is a function. Okay, so it's a family of functions. It does not give us a numerical answer. Okay, so and that's always a good thing to check with yourself when you're doing a problem, right? Make sure that the answer you get matches, right? If it was a definite integral, your answer should be a number, and if you had an indefinite integral, your answer should be a function. Okay. Here's a table of a bunch of indefinite integrals. So first up, they have a lot of the different properties that we talked about. We have there's a bunch of different kinds here. Here's the scalar multiplication, there's addition rule, we have antiderivative of a constant, right? Undoing the power rule, e to the x, a bunch of trig ones here. Okay, a lot of trig, some inverse trig, hyperbolic trig. So a lot of different antiderivative formulas here, but all of these we can derive just by remembering what the derivatives are of those original functions, and that'll get us the antiderivatives. Okay? So let's do some more examples. Right, so find the general indefinite integral for this function. So antiderivative of x to the fourth, that's going to be x to the fifth, right, because I'm going to add 1. And my shorthand, I noticed that this 10 has a 5 in it, so I'm going to take the 5 and move it up here, and I'm left with a 2. So that's going to become 2x to the fifth. Okay. Or if you don't like thinking about it that way, you can say, add 1 to the power and then divide by that same number. So, and then the 5 down here cancels with the 5 in there, if you like to think of it that way. Okay, so that's the first one, and then minus the multiple of 2 is just tags along. Antiderivative of secant squared of x. Okay, so that's a function whose derivative is secant squared. So that would be, hopefully we remember, that's tangent. So we get 2x to the fifth minus 2 tangent of x plus c. Okay, let's look at this next example. So evaluate the integral. So we have x cubed antiderivative, that's x to the fourth over 4, minus antiderivative of x is x squared, and I'm going to take the 2 out of the 6. So that's going to leave me with a 3x squared. And this one, because we have bounds, we're going to evaluate from 0 to 3. You don't need to include the arbitrary constant when you're doing a definite integral. However, you can. If you'd like to include the plus c, that's fine. It's just that you're going to get the first term with a plus c, and then you're going to subtract off a plus c, and it's going to disappear every time. Okay, so you don't have to include the plus c on a definite integral, but you can, and then it'll just disappear in your calculation. Okay, so this one, let's evaluate this. So we have 3 to the fourth over 4 minus 3 times 3 squared minus 0 to the fourth over 4 minus 3 times 0 squared. So that whole second term is going to be 0. You do want to write it out, though, because sometimes it won't be 0. And you never want to just assume that it's 0. Okay, so that's going to give us 3 to the fourth is 81 over 4 minus 3 cubed is 27, which gives us negative 27 over 4. And that would be the value for this integral. Notice, of course, that we have here a definite integral that had bounds back in the original function, and we got a number. Right? We got a numerical answer for this one. Okay, let's look at the next one. So evaluate this integral from 1 to 9. So for this one, it's a good thing to take notice that this function is very complicated, but it can be simplified, right? So rather than just trying to dive in and take some really complicated antiderivative, we need to simplify this algebraically first, and then we can start working with it. So I'm going to leave the integral there, not do anything with it yet. Each of these can get split up over that common denominator. Okay. So, sorry. These middle two are one term. So these come together. Okay, so we have 2t squared over t squared. That's just 2. We have t squared times root t over t squared. So that's just plus root t. And then minus 1 over t squared. dt. Okay. And then to make this even a little bit easier, let's go ahead and just write everything in a form that we can work with a little more nicely. So that's going to be 2 plus, instead of root t, I'm going to write t to the 1/2. And then minus, I'm going to write this as t to the negative 2 power. Because now all I need to do is undo the power rule on all three of those, and then we'll be good to go. So the antiderivative of 2 is 2t. Antiderivative of t to the 1/2 is going to be t to the 3/2 divided by 3/2. Okay, but instead of dividing by 3/2, I'm going to multiply by 2/3. So that's 2/3 t to the 3/2. And then for t to the negative 2, we're going to add 1. That becomes t to the negative 1 over negative 1. So that's going to become plus 1 over t to the first. Okay, so a bit of algebra being done in there. So we get this, and we're evaluating it from 1 to 9. Okay, so let me just set this up here. So that's going to be 2 times 9 plus 2/3 times 9 to the 3/2 plus 1/9 minus 2 times 1 plus 2/3 times 1 to the 3/2 plus 1 over 1. If you combine all of those, it's going to get a little messy. You're going to have some fractions you're working with in there, but the exact answers are always better. We're going to get 292 over 9. So 292 over 9. That's what we get out of there. Okay. So, which is kind of an ugly number, but it is the exact answer, which is something that makes this very powerful, is that if we were trying to approximate this, it would be very hard. We'd have to do a lot of rectangles in order to get an approximation that we would be convinced is close enough to 292 over 9 without being able to find it exactly. So, okay, let's look at another one. All right. So evaluate the integral from 1 to 9 of 2t cubed minus 6t plus 3 over t squared plus 1 dt. So with this one, let's take the antiderivative of each of these parts. So this is going to become t to the 4th. And it would have been over 4, but remember there was a 2 over here. So it's going to be 2 over 4, which is just 1/2. So that's 1/2 t to the 4th minus 3t squared plus 3 times, so 1 over t squared plus 1. That is the derivative of a function. And hopefully, does anybody remember what that function is? Right? The derivative is 1 over t squared plus 1. That's going to be inverse tangent of t. Okay, so we get the inverse tangent function there. And then this gets evaluated, all of it, from 1 to 9. Which this one, I'm not so worried about all of the brute force on this one, because this number is kind of high, especially with the 9 in it, and then the inverse tangents and whatnot. But I'll just give it to you what the answer would be if you were to go through this. I'm more concerned with your ability to get to this step, okay, being able to take the antiderivatives appropriately, and of course, given smaller numbers, I would expect that you could do this on your own. But for the sake of time, I'm just going to give this to you. So we would get 640 minus 3 pi over 4 plus 3 times inverse tangent of 9. So that would be the answer that we'd get. Okay. Now, similarly, we have the same function, but evaluated for different bounds. So the nice thing about this is it doesn't change the antiderivative at all. So this would be 1/2, except now it's in terms of x's. So we have 1/2 x to the fourth minus 3x squared plus 3 inverse tangent of x, evaluated this time from 0 to 2. Evaluate that, we get -4 plus 3 inverse tangent of 2. That would be our exact answer. Okay, now if we were looking at this in terms of the areas, try to make a determination here. Notice we have some positive area up here, and again some more positive area over here, and compare that to the negative area down here. So to me the negative area looks a little bit bigger than the positive, so I would expect this to be slightly negative, not too terribly negative, but slightly negative. And if we can just plug and chug this number in a calculator, we get this is approximately -0.679. Okay, so that would be our approximate value. Again, when we're doing calculations, exact answers are always better, but just to get an idea, the visual of what's happening here, it is a negative area. It's only slightly negative. So, all right. So let's look at an application. So we've been looking a lot at the concept of velocity, distance, position, right, acceleration, all that kind of stuff. So before, what we were looking at was the concept that if I have a position function, then I take its derivative, it gives me velocity. And then, of course, with antiderivatives, we go backwards and we say, well, now what if I have velocity? That can give me distance. So what we can do now that we can evaluate integrals directly is we can say, based on the net change theorem, the integral of a rate of change is the net change over the interval. Okay, so when we say net change, we're talking about total change in f between a and b, so that's f of b minus f of a. So net change takes into account both positives and negatives. So, because you could have positive velocity and negative velocity, right, moving forward, moving backwards. So when we say net change in distance, we're talking about your distance from where you started. Okay, so if I am, at home and I'm going to drive in a straight line to work, and I make it halfway to work, and then I realize that I forgot something at home. So I turn back around, come back home again, and then drive back to work. That's the actual amount of miles that I've driven, right? I drove halfway there, halfway back, and then all the way there again. So I've actually done the equivalent of 2 trips, right, to work. But my net distance is just, right, 1 trip to work, right? Because I end up just being, however far it is, 10 miles from where I started, instead of saying I drove 5 back, and then drove 10 more. Okay, so positives and negatives can balance each other out when we're talking about net change in distance. Okay, so, and this is what all of this is talking about. So rate of growth of a population, of volumes. This is the one that we primarily work with. So the motion of a particle. Okay, so, or movement of anything. Okay, so this net change is also called displacement. So that's a good word to remember if you see the word displacement. This is what we're talking about. Okay. Now, if we want to compute the total distance traveled by an object, okay, so like I mentioned in my scenario, so I'm driving 10 miles to work, halfway there I forget something, so I turn back around. My net distance after I've gone 5 miles out, 5 miles back, and 10 miles back to work, my net distance is only 10 miles, right? I'm 10 miles from where I started, right, from home to work. But the total distance that I've traveled, right? If you look at the trip meter on the car, the odometer, I drove 5 miles out, 5 miles back, that's 10 miles, plus another 10 miles to work. So I've actually driven 20 miles on the car, right? But the net distance wouldn't tell me that, right? It only tells me I'm 10 miles from where I started. So we need to be able to compute what we call total distance traveled, which takes those negatives into account and counts them as positives. Okay, because I need to know that I went 5 miles, then 5 miles, then 10. Okay, the way that we can do that is by taking any of the negative distances and make them positive. How do we make something positive? By taking an absolute value. So here's what we're doing. We are, in order to get the distance an object travels, we take the integral of the absolute value of the velocity function. Okay, now when we talk about taking the absolute value, you have to be careful. These problems usually require a bit more work because we need to know where the function is positive and where the function is negative. Okay, that's the only way that we can actually evaluate them properly. Because if you just take every negative and make it positive, you might have actually changed the numbers, okay, without even realizing it. So down here you can see more of a visual representation, right? So our displacement is where you take the positive area up here and here, A1 and A3, and then subtract the negative area. Whereas the whereas the total distance traveled, you take the positive area and the other positive area, and you then add that negative area in. And you count it positively because even though it was the opposite direction, it was still distance being traveled. Okay? So hopefully this is making sense. If it's not, let's look at an example. Maybe that'll help. So an object moves along a line so that its velocity at time t is v of t equals t squared minus t minus 6. So it measured in meters per second. So first off, find the displacement of the object during the time period from 1 to 4 seconds. Okay, so our displacement, that's going to be the integral from 1 to 4 of the velocity function. So t squared minus t minus 6 dt. So take the antiderivative. That's going to be t cubed over 3 minus t squared over 2 minus 6t evaluated from 1 to 4. So that's going to be 4 cubed over 3 minus 4 squared over 2 minus 6 times 4 minus 1 cubed over 3 minus 1 squared over 2 minus 6 times 1. If we run that computation, we're going to get negative 4.5, and this is in meters. Okay, so the displacement of the object over this period is negative 4.5 meters. So in other words, it traveled from 1 second to 4 seconds. If you compare where it started to where it ended at 1 second to 4 seconds, it is 4.5 meters behind where it started. Okay. But if we're looking now in part B at the distance traveled during this time period, then you can see the graph down here, right? So it's going backwards for quite a ways, and then it turns around and starts going forwards up here. So for the distance traveled, we need to take the absolute value of this function, but in order to do that, we need to know where the function is positive and where it's negative. Now, of course, you can see on the graph right there, but we wouldn't normally have a graph given to us, so we need to actually compute this analytically. So let's look at the function. So v of t, so it was t squared minus t minus 6. That is actually factorable as t plus 2 times t minus 3. And I'm going to set that equal to 0. Okay. What am I looking for? I'm basically looking almost for critical points here. So that gives me t equals negative 2 and t equals 3, right? Because this is where the velocity is 0. This is where it's changing direction, right? Going either positive to negative or negative to positive. Now, The -2 we don't care about because we're not dealing with negative time here. We only care about the 3. So if we just run this real quick, check a value to the left and to the right. So pick like 2 and 4, for example. You're going to find we get negative velocity, then positive velocity. And again, you can see that over here on the graph, right? You have negative and positive, which means we need to compute the area in the positive up here, and then compute the area in the negative down here, and then once we get this negative area, we need to make it positive. Okay? And that's how we're going to compute that distance traveled, is take the negative area and make it positive. So we need to get the integral from 1 to 4 of the absolute value of t squared minus t minus 6 dt. So, and like I said, this is not as simple as just taking all the negatives and making them positives. It doesn't work that way. That would actually give you a totally different wrong answer. So let's split this up. So the negative part is going to be integral from 1 to 3. Okay, and then we're going to take, the function would normally give us a negative value, so I'm going to make it negative myself. So t squared minus t minus 6 dt. Okay, so again, just as a reminder, this value is going to be negative. So to make it positive, I'm putting a negative in front of it so that the two negatives will cancel in the end. Okay, and then add on that positive area, that's from 3 to 4 of t squared minus t minus 6. And this one's already going to be positive, so we don't need to mess with it at all. Okay, and then take the antiderivative. So we get negative t cubed over 3 minus t squared over 2 minus 6t from 1 to 3 plus, and then we get the same. So it's all the same antiderivative here. Minus t squared over 2 minus 6t, evaluated from 3 to 4 on this one. Okay, so you would be doing, right, that evaluation from 1 to 3 on this one. Don't forget to make it negative, right? Don't forget that negative out there, or else you're going to get a negative answer, and that's not going to work out. And then evaluate this one. And when we do this, this is going to give us 61 over 6, which is approximately 10.167 meters. If I can get in there. Good enough. So 10.167 meters approximately. So what does this tell us? Well, it tells us from second 1 to 4, the object from start to finish ended up 4.5 meters behind where it started, but over this time period it traveled over 10 meters. Okay, it just so happened that some of those meters, more of the meters, were negative, they were backwards, okay, and then a few of them were positive or forwards. Okay, so we get the difference here between net distance and total distance traveled. Okay, so and that is going to be it for